Hello, my name is Kelly Caldwell and I'm the lead instructor at Stanley Community College's Instructor Training Center. This is going to be a lecture on one of the many modules in the different courses inside of Cisco Networking Academy. I'm going to cover many different items in these particular lectures, starting with CCNA, going possibly all the way through DevNet. But to begin with, one of the things I want you to know is I go with a good enough philosophy, and that is no lecture is perfect. So in other words, if you're in the classroom with me, we could be interrupted by a person knocking on the door, my phone could ding, your phone could ding. I'm not going to have perfect lectures, and therefore my recorded lectures will not be perfect. You may hear my phone ding, you may hear a phone call start during one of the lectures, and I'll pause the lecture and then start back over. I'm trying to give you a good enough lecture to help you learn the materials. I also want you to know if you are not taking classes at a Cisco Academy, in other words, you're watching these videos on my YouTube channel and you're not trying to participate in an actual Cisco Academy, I strongly recommend that you go to www.netacad.com, scroll all the way to the bottom to where it says Find an Academy. I'm going to put in here the state, city that we are in. So in case I am in Albemarle, NC, North Carolina, as you can probably tell by my accent. But you'll see here Stanley Community College, and if you click here, you would get the information on what courses we offer and how to get in contact with us and how to actually see our offerings. So if you are in an area and you would like to find your local school or Cisco Networking Academy, then go to netacad.com, scroll to the bottom, and do Find an Academy. I strongly recommend that you get involved in the Cisco Networking Academy because it is a wonderful, wonderful program. Last but not least, enjoy, learn, and grow. So enjoy these lectures, learn from them, grow. If you want to grow in the IT field, that's excellent. Or if you just want to learn new things, that's even better too. We hope these lectures will be useful for you and that you will be able to use them to increase your knowledge in the IT field. Hello and welcome to a lecture on Module 7 of Introduction to Networks version 7.02. This module talks about Ethernet switching. In particular, we're going to look in detail at 802.3 Ethernet and the Ethernet frame format that is associated with 802.3. We're going to talk about MAC addresses, what they are and how they're used. And we'll also talk about how switches, which are layer 2 devices, both build their MAC address table and use it to forward frames. And then some of the different methods that switches use in order to forward frames. First off, Ethernet has come in many different flavors and still comes in many different flavors. By that, I mean it had started out at 10 megabits per second. And it's all the way up to 100 gigabits per second now and even faster. The good news is, as the OSI model is created and the way it is created, it's because of the fact that the data link layer is broken into two sublayers, the logical link control sublayer, which I discussed in detail in Module 6 lecture, which is the software interface between your hardware components and your upper level software components at the network layer. And the MAC layer, the 802.3, because of these sublayers, we can and have been able to continuously update Ethernet with faster and faster speeds and just have it interface with this logical link control sublayer without having to completely rewrite the entire Ethernet data link protocol. So the LLC sublayer again is that interface between your hardware components at the MAC address layer, at the MAC sublayer, and the complete software components at the network layer. The MAC address sublayer is actually responsible for data link addressing. We'll talk about MAC addresses here in a second, along with the different access methods we discussed back in Module 6, such as carrier sense multiple access with collision detection, and CSMA-CA, which is carrier sense multiple access collision avoidance. Those are the two main methods that we are aware of with both wired Ethernet and wireless Ethernet. Again, the MAC sublayer, it deals mainly with framing. So we're going to look at the structure of an Ethernet frame and how it is designed. We're going to look at Ethernet addressing, so MAC addresses and what makes up a MAC address. And then at the end of each Ethernet frame, there is what is called a frame check sequence, or a CRC in some books. But basically, it's a mathematical equation that's run against the frame before it's set and attached to the frame, and then on the receiving end you run the same mathematical calculations. An integrity check is what it is, and if it's the same on the receiving end, then the machine assumes the frame was not damaged and or changed during transit. Here is the Ethernet frame. This is, you'll notice that Ethernet frames have a minimum size of 64 bytes, which is why anytime a machine sees a frame below 64 bytes, it's called a runt, and it's typically the result of a collision or because it's a fragment. And then a maximum of 1,518 bytes, 1518 bytes. That includes all the bytes through the frame check sequence. So if it's above 1518, many different devices will see that as a jumbo frame and will actually ignore it or kick it out as an error. However, you will learn in data centers, we've been able to actually use what's called jumbo frames, larger frames, because we have very high speed switching devices inside of our data centers. We've been able to use jumbo frames because we know there's very little error, very few errors going through those networks. But be aware, if it's smaller than 64 or greater than 1518, most typical Ethernet devices will see that as either a runt or a jumbo frame. The Ethernet frame field has in it an 8-byte preamble and starter frame delimiter, which you'll learn is basically a starter frame delimiter. It's a sequence of bits that symbolize a frame is on the line. Then you have 6 bytes, which is the MAC address, which remember I told you they were 48-bit addresses. Well, 6 bytes is 8 times 6, 48 bits. So you have your destination MAC address first. That goes back to the discussion I had last lecture where I talked about the reason the destination MAC address is first is because in our old networks, you'll notice this is an old bus network. It used to be that every device, when a frame went by it, every device had to look at that frame at least up to the destination MAC address and find out if its MAC address was the destination MAC address. Well, if we put the destination MAC address first, if a device looks at it up through the destination MAC and sees it as not destined for it, it can just immediately discard it. So it makes no sense to put the source MAC first, as then you would require more processing at layer 2 than would be needed for a frame that was going to be discarded anyway. We have a type length that passes it up to a layer 3 protocol, 0x800 for IPv4, 0x86DD for IPv6, and if you're doing address resolution protocol, which you'll learn more about later, 0x806. And then we have the data field, which this is all the information from the layers above layer 2, which are inside of here. So this would have all your application header, it would have your network layer header, transport layer header, everything is inside of here as data. And then of course that frame check sequence, which is at the very end. Okay, so let's look at MAC addresses. MAC addresses are placed in hexadecimal. And so hex, as you remember from our discussion a couple of modules ago, is a base 16 numbering system. So it uses a number 0 through 9 and then A through F to represent 10 through 15. You'll see binary 0 through 15 or decimal 0 through 15, binary 0 through 15, and then hexadecimal will give you, those are the equivalents here. So when you look at a Ethernet address, you're going to see it as hex. And so it's written as 2 hex. It really depends. Sometimes you see it as 2 hex dash or hex dash hex dash. Sometimes you see it as 4 hex bits dot 4 hex bits dot. Depends on the device itself. In our examples, typically what you're going to see here is you're going to see each hex set of hexes are separated by a dash. And you'll notice that in a MAC address, there are 48 bits, but 24 bits of that are actually what are called the organizational unique identifier. Now, the OUI is interesting because if you look at frame captures inside of Wireshark, you look at it and some other things, it will typically actually try to tell you who the manufacturer of the device is. So every NIC that is created that has a unique MAC address on it will actually have 24 bits that relate to the manufacturer. So that's one of the reasons why you can actually be tracked by your MAC address if you're not careful. So the first 24 bytes will be your OUI. The last 24 bytes are the vendor assigned serial number. This was, by the way, how they found the Bind BTK killer. He had actually created a document, and in that document was the MAC address of the machine it was created on. They used that to identify that it was a Dell machine or a particular brand of machine. and then the vendor assigns serial number, and then they track down who purchased that machine. So if you can get from a security standpoint, the MAC address of the device that has sent a frame, you're able to track to a very, very close detail who has or who owns that device. So in frame processing, you'll notice as with switches, you need to send information over to H3. You would frame it. You'd put in the destination frame, you'd put the MAC address of H3. And then if this was actually a hub, now in a true switch network, this frame would not have gone over to H2 and H4. I love how it's kind of old English. This is not addressed to me. I shall ignore it. But if this was a hub, this is exactly what would happen. It would go out all the way down on each one of these. Each one of these would look at the destination MAC and go, hey, that's not mine, and would ignore it. We're going to learn that switches actually build what are called MAC address tables. And then using that MAC address table, they're able to only send frames from the correct source to the correct destination if they know it. Now, as we look at MAC addresses, there are really 3 different types of MAC addresses. One is a unicast MAC address, and that is a MAC address that is assigned to a single device. So if it's the destination MAC address of 0007E9, by the way, that's the OUI for this MAC address, 42AC28, which is the serial number of this MAC address, then that would be the destination MAC address of this server at 1.200. So if in the frame it has a destination MAC of a single device, that's considered a unicast MAC address. If the MAC address is to a broadcast, so it's all Fs or all ones, this is a special MAC address that when it goes out would actually be seen by everyone on this switch. So the way a switch works by default, anytime a broadcast MAC address comes in, it goes out every port except for the port that it came in on. Unicast is different. Let's go back up here real quick and I'll show you unicast. Unicast would come in, the switch would do a lookup in its MAC address table, also sometimes called the content addressable memory table or CAM table. And then it would see that this server was off this port right here and would send it only to that one server. So in a properly functioning network, H1 can send directly to this server and no one else is affected by that frame traffic. However, if you send a broadcast, every other device on the network sees it. So you have to be careful with broadcasts. Broadcasts are bad. That's what I teach my students. Now, that's not to say you can do away with all broadcasts, but it is a fact that we try to reduce broadcasts as much as we can. So unicast is 1-to-1, broadcast is 1-to-all, and then multicast is 1-to-some. And so these would be destination MAC that would be associated with typically some type of application that is running on a device. And with we can actually do what's called multicast pruning. We could even set up where these 2 devices would not even see these multicast frames because they would not be part of the multicast group. But this is some multicast is a 1-to-some, so it's a special group membership. So let's look at a MAC address table on a switch. By default, by the way, the first thing that happens is a switch's MAC address table is completely empty. And because of that, when a switch first boots up, it really acts just like a hub. In other words, if A with, and these are shortened MAC addresses just for simplicity's sake, but let's imagine that A was going to take something, was sending something to B. Let me do this real quick. I'm actually going to grab a quick snip this out. Okay, so let's say that right now we have a situation where our switch has just booted up. You notice there's nothing in the MAC address table. A wants to send to B. Well, A would create well, what's really going to happen is A is going to send what's called an ARP request. It's going to say, hey, I need the MAC address for B. And that would get flooded out all ports except for the one it came in on. Once A knows B's MAC address, it would actually send a frame that would have in the frame header the destination MAC, which would be, in this case, B's MAC, and the source MAC, which would be A's. But the problem is, because this particular switch is just booted up and has nothing in its content address memory table or its MAC address table, that frame would come in, okay, to here. Now, what would immediately happen is the switch would say, oh, on this incoming frame on port 1, the MAC address 00-A0A is on that port. And so it looks at the source MAC address and knows that that is on that port. It would then flood it out every port except for the one it came in on because it doesn't know who's supposed to get it. C and D would ignore it because it's not their destination MAC address, so it would just ignore it here. B would respond, and when B responds, the switch would then build the MAC address table and say, oh, B is on port 2, the MAC address is 000B. And then it would continue so on and so forth to build the tables for 3 and 4 until it had a full MAC address table. At that point, once that's done, what happens is this. If A needs to send to B, it comes in. The switch does a lookup and says, oh, that's destined for the MAC address 000B, and would only send it out port 2. Okay. But a switch that's just booted up will act like a hub and send it out all until it builds its MAC address table. So it's going to learn each one of these. It learns as it looks at the source MAC addresses. So there again, and then it would send it out all of them, just like I said, and it would, by looking at the return information, figure out that B is on port 2. And eventually it's going to learn that A, B, C, and D, where they're on each one of these ports, and it will be able to send directly. In addition, it will allow A to send to B while C is sending to D by using what's called its port buffers. So here we have an example of a PCD responding back to PCA, and because the table has been built, that will go directly from PCD over to PCA. It will not affect any other devices because the table knows where each one of these devices resides, or not the table, the switch knows where these devices reside. There's a couple of videos in the curriculum that you need to watch, but I really love this. One of my favorite activities right here in the entire curriculum, because it forces you to really think about what is going on. So we're going to look at this and we're going to say, look at each one of these, determine how the switch will forward a frame based on the source MAC, the destination MAC, and the information in the switch MAC table. So the frame has a destination of 0A and a source of 0F. Okay, so it's right here and it's coming in here. Now, by the way, that's a hub. That's a hub. So that means on port 9, this switch will eventually know that, or does know in this case, that 0A and 0F are both on port 9. But now let's look. As you look for the destination of 0A, you'll notice that's nowhere to be found in the MAC address table. Okay, so because of that, the fact that it does not know where to send it, it's an unknown MAC address. In that case, it's going to send it out every port that is in use except for the one it came in on. So in this case, it would send it out FA1, it would send it out FA3, it would send out FA5 and FA7. And it's going to say switch adds the source MAC address was currently not in the MAC address table. Well, if I look right here, the source is 0F. No, that's already in the MAC address table, so that's not true. The frame is a broadcast. That is not true because it's not all Fs. It's not FF. Frame is a unicast. We've sent only to a specific port. It is a unicast, but it can't be sent to a specific port because we don't know where that device 0A resides. Frame is a unicast. It will be flooded to all ports. That's the correct answer. It's a unicast to be dropped at the switch. That is not true. Check it, and you'll see that is correct. Now, the great thing about this activity is you go new problem. So now the frame is 0C is the destination, 0B is the source. So we look here at our table and go, okay, well, that's a unicast. So is 0C in the table? The answer is yes. Well, that means that it will be sent directly just to 0C, which will be port FA5. Is it going to add the source MAC address? No, it's already in the MAC address table. 0B is. It's not a broadcast. It's not all Fs. It's a unicast and be sent to a specific port. That is correct. It's not a unicast that will be flooded because the destination port is known. We know where that's at. It's off FA5 and it's not going to be dropped. So here we go. Check it. New problem. And you can keep doing this, so on and so forth. So again, 0D, 0A. This one would be a, it's only going to go to 0D, which is FA7, and it's going to send to specific port only. Oop. Oh, wait a minute, I messed up. 0A is not in the MAC address table, so it's going to add it to the MAC address table. There we go. So 0A was not in the MAC address table, so it has to send it. Has to put that in the MAC address table, and now it's correct. Okay, what did I do wrong here? So destination is 0D. 0D is an FA7, which is correct. Switch adds the source MAC address, which is currently not in the MAC address table. Source MAC, that is true. It's not a broadcast. I think this one may be graded wrong. Yep, it's grading wrong because this is the correct answer. Yep. So when I didn't, it had graded it, didn't know that the correct answer is switch adds it to the MAC address table and the frame is unicast sent to a specific port. So that was just a little quirk in this activity. But so that is a neat activity that allows you to learn how a switch works with a MAC address. So remember what happens with switches. Number one, if it's a brand new switch, it has to flood it out all ports except when it come in. If it knows where the destination MAC address is, what port it is, it'll send it directly to that port. It will then also, every time it sees a MAC address that comes in as a source MAC address on a port, it will add that to the table if it's not already in the table. So on Cisco switches, we really have two different types of forwarding frames. One is called store and forward, and that's where you actually bring the entire frame in, run the CRC, ensure the CRC is valid before you send the frame out to the egress port. The big thing about store and forward is you never have to worry about accidentally sending a frame that has been already damaged in transit, because or should not have been damaged in transit unless it's damaged from the egress port to the destination. Cut through, though, is a faster way of doing it. With cut through, there are two different ways of doing it. Let's look at store and forward first. With store and forward, you bring it in to the switch, you look at the entire frame, run the CRC, make sure it's good, then do your lookup, then forward it. Okay. In that case, you never have to worry about forwarding a frame that has been damaged coming into the ingress port. Cut through switching has two different ways of doing it. One is it's called fast forward, where it can start forwarding as soon as it gets at least the destination MAC address. Or another one called fragment free, which relies upon a characteristic of Ethernet that is anything bigger than 64 bytes should not be a collision, should not be a runt. So those are two ways, and it's a little bit quicker because as soon as you get the destination MAC, it starts forwarding. Now that does mean that the receiving end could receive a frame that had been damaged in transit and would be dropped at the destination due to it failing a CRC check, but that is something that rarely occurs. So fast forward and fragment free are quicker methods than store and forward. Store and forward, though, if it's possible for the switch to do it, is a method that guarantees you're not going to send a damaged frame. We also have on each of our switches or in switches buffering on the ports themselves. This allows, for instance, if on our particular networks, if PCA is sending something to B while D is sending something to A, the switch can actually buffer that communication so that you don't have collisions. There's two types of buffering. One is port-based memory, which is memory that is assigned to every single port and is only for that one port, or shared memory, which is basically a shared memory pool, so that each port can use the shared memory in the shared memory pool. The problem is if you run out of shared memory for your buffers, then you could end up with performance problems with your ports. So be aware of that, those two methods. And we talked already about this, full versus half duplex. Full duplex, you can either send or receive. Excuse me, half duplex, you can either send or receive, not both at the same time. So again, base camp to camp 2 OVA, telling them they've got to now respond. Whereas full duplex is you can send and receive simultaneously. When you connect a device to a switch, it's going to negotiate or can auto negotiate whether it's full or half duplex. It can also auto negotiate speed. Typically, I like to set on the switches themselves the speed in duplex and not let them auto negotiate. That way you don't end up with auto negotiation issues. That used to really occur mostly on things like fax machines and older printers. And then we also have what's now called auto MDIX. It used to be that if you connected like devices, in other words, if you connected two switches to one another, you had to use a crossover cable. And that's where you took pins 1 and 2, 3 and 6 and rotated them or switched them over for a crossover. We no longer have to do that. You don't have to do a crossover cable. There's a new thing called auto MDIX or auto cross, and most modern devices now allow you to put a straight through cable even between like devices. Just be aware if you've got an older switch like a 2950 or an old switch, you may actually get into problems if you try to connect two switches together and they do not support auto cross or auto MDIX. And that is it on Ethernet switching. I hope this has been helpful and helps you again as you begin your studies on CCNA and switching.